Go ahead and start recording. Okay, like I said, y'all, I'll have two videos, two separate videos, one for 3-4, one for 3-5. Okay, so 3-5, y'all talks about derivatives of trig functions. So we're going to find derivatives of sine and cosine functions, the other uh, standard trig functions, and we're going to also calculate higher order derivatives of sine and cosine. Okay, so when we were here in class on Monday, and we were doing like the derivative of a product. We said it's like the first times the derivative of the second plus the second times the derivative of the first, and then we kind of applied that to what happens when we have three functions, something like that. I was kind of going through the whole like theory or whatever behind it, kind of see how we could derive some of those things. But what I decided for 3-5 is instead of us going through like the proof of the derivatives, I'm just going to give you the tables that have these derivatives, and then we're just going to apply them basically, okay? So I'm going to kind of scooch down over here, and what we have here, y'all, in theorem 3.8 are the derivatives of the sine function and the cosine function, okay? So instead of going through the whole process of how do we actually end up with this, this is the really important part, okay? So the derivative of a sine function, y'all, is a cosine, and the derivative of a cosine function is actually a minus sine function, okay? So for the first one that I have here, y'all, it says we're going to take the derivative of f of x when f of x is 5x to the third times sine x. Okay, so remember, when we have a function, and this is a product, y'all, I can think of this as 5x to the third times sine of x, and we're going to find the derivative. We're going to find f prime of x. We said we're going to take the first function, which in this case is 5x to the third, times the derivative of the second. What is the derivative of the sine? Cosine x. So we're going to write here cosine x, plus we're now going to take the derivative of the first function. What's the derivative of 5x to the third? 15x squared times just the second function by itself. And the second function was just sine of x. And that's it.
No combining?
No combining. I can't really combine them because one's a cosine, one's a sine, right? So I can't combine them. Can I factor stuff? Yeah, but you don't need to worry about factoring stuff. Okay. Yeah. Okay, so look what else we got right here, y'all. I also have the derivatives for tangent, cotangent, secant, and cosecant. So the derivative of a tangent function is secant squared. The derivative of cotangent is a negative cosecant squared. The derivative of a secant function is secant times tangent, and the derivative of a cosecant function is a negative cosecant times cotangent. Okay? All right, so let's see if we can figure out how we're going to do this problem here. So it says if f of x is equal to cosine x minus 5 tangent of x, we want to find the first derivative. Okay? So let's see if we can find f prime of x. We're going to go through slowly. Okay, let me see. Let me scroll back up for 1 second, y'all, because I'm going to make sure you can see this. I want to take the derivative of cosine. So if I scroll back up here, where is it? Oh, past it. Here we go. What's the derivative of cosine? Negative sine x. Okay, so I'll tell you what we're going to do just to make things a little bit easier as well. I'm going to go right here. Let me do that. Let me copy this guy here. And I'll do this. And I'll do this. Okay, and so right over here, y'all, I'm going to put this part just so that we got it over here too. Okay. Okay, so we said the derivative of a cosine is a minus sine. So right here, I'm going to write negative sine x minus 5. What's the derivative of tangent? Secant squared x, right? Okay, so this part right here, y'all, is my answer for the first part. You're just taking the derivative, right? You're taking the derivative. Why are you looking at me? Why are you looking at me so? No, not doing anything right now. Just take the derivative, plug it in. Okay, now I want you to look at the next part. It's asking us to find f prime at 3. What does that mean I'm going to do? Just plug in a 3 for x, right? Okay, so negative sine times 3 minus 5 times secant squared at 3. Okay. Now, y'all, I want to mention something. When you're going to do this part here, you're going to do this obviously on your calculator. Okay, your calculator needs to be in radians. Okay, since remember, if you're talking about real numbers, if you're evaluating these things at real numbers, they're always going to be, my calculator always needs to be in radian form. So I'm going to show you something here, y'all, on how to evaluate this. Now, my question to you is, does anybody remember the relationship between secant x and cosine x? How is the way that I can write secant is the same thing as something with a cosine? Does anybody remember? Say it again? Well, it's 1 over cosine x, okay? So yeah, secant x, guys, same thing as 1 over cosine x. So I want to show you something here. And I'm talking about this because when I'm going to get to the evaluating part, I'm going to leave my 5 alone. I'm going to write this as cosine squared at 3. The reason why I'm doing this is when it comes to evaluating the function, I think it's going to be easier in terms of how do you actually plug this into your calculator, okay? So look, I'm going to turn on my calculator. Let me clear this out. First thing, y'all, I need to make sure that I'm in radians. So just to give you a heads up, if you're doing this on a TI or whatever, you're going to hit mode. Make sure that you are in radians, okay? So I'm in radians there. Okay, so now we're going to say negative sine at 3, okay, minus 5 over parentheses cosine of what value? What are we evaluating at? 3. And because it's cosine squared, I got to square that part. Okay, I'm going to hit enter, and I'm coming up with negative 5.2427, right? So I'm going to enter in negative 5.2427, and I'm done. 2427. Okay. Should be. Okay, you coming up with the same answer I did? Then it is, right? Yeah. Okay. All right. Let's try another one similar. Let's see. Okay. Find the equation of the tangent line to the curve y equals 2 sine x at the point pi over 6 and 1. Okay. So let's see if we can do this. Remember, y'all, if we're looking for the equation of the tangent line, the first thing we need to do is we need to find the derivative, right? Okay, so we're going to take the derivative of 2 sine x. Okay, so again, let me scroll back up here just so you can kind of see it. What did we say the derivative of a sine function was? Cosine, right? Okay, so the derivative of sine is going to give me cosine. So wouldn't this be 2 cosine of x? Because I got that 2 in front, right? I can't forget about it. It's still there. Okay, now the other thing I want to mention is, remember the point that they gave us? The point that they gave us was pi over 6 and what? And 1, right? Okay, so if the point they're giving me is pi over 6 and 1, that means, isn't this my x value right here, guys? That pi over 6? Okay, so I need to find the derivative at pi over 6. So I'm going to take the cosine of pi over 6. Now, y'all, it depends on what kind of calculator you have. I have an older calculator. I got a TI-83. I know John has a calculator that's a little bit newer. But one thing I wanted to mention was Remember I told you all today that here in the content folder, I included a table of trig function values, right? So I'm going to access that, okay? So let me come back to my notes, right? But here is the table of trig values, okay? I'm trying to find what the cosine of pi over 6 is. So look, if I come over here, here's cosine, here's pi over 6. Cosine of pi over 6 is square root of 3 over 2, right? So you guys have access to this, right? So I gave this to you guys. I put it in your notes so you can access it, right? All I'm doing is pi over 6 at cosine, square root of 3 over 2. Yeah, we'll get there in 1 second. Let's see. Y prime at pi over 6 is 2 times the square root of 3 over 2. John says those 2's are now going to cancel. So y prime at pi over 6 is just the square root of 3. Does that make sense? Jennifer, am I doing okay? Okay, just checking with you. Okay, question, guys. What did we just find here? Anybody know? Is that the equation of the line? Okay, so hold on. Let me ask you a question. What? Hold on. Go slow. Hold on. What does the derivative tell me to do? When I'm finding the derivative, what am I finding? I'm finding the slope. So we found the slope of the tangent line. Okay? So the derivative is telling me, how do I find the slope of the tangent line? I want you to look at the first part of this thing right here. It says the equation of this tangent line has a slope of, what number did we get? Square root of 3. That's what I'm going to write right there. Okay? Square root of 3. Now we want to find the equation of the line. Okay? So remember, y'all, the way we find the equation of our line is we use this formula right here. Okay? Do y'all agree with me that this is my x1 and this is my y1? Right? Okay, so we're going to go y minus, what's y1? 1 equals m. Did we find m already? Square root of 3. Excellent. Parentheses, x minus pi over 6, right? Okay. So now, y'all, I'm going to write this as y minus 1. You agree I have to distribute this? Square root of 3 with an x minus, if you're wondering, how do I multiply the square root of 3 times pi over 6? Pi square root of 3 over 6. Can't really do much more with them than that, right? Now, guys, I want to emphasize something here. The only reason why I put the square root of 3 at the end is so that it doesn't look like the pi is inside the square root. You see what I mean? I didn't want to put the square root of 3 and then the pi, because then sometimes people say, hold on, is that pi inside the square root? No, it isn't, okay? So when I put the pi in front, then we know the pi is not inside that square root, okay? Yes, we can put the x second. Yeah, we can definitely do that too. So we could do this if we wanted to. If we wanted to put the x right here, yeah, we could do that too. That's a good point, because we don't want to have the x inside the square root, right? It's not inside the square root. Okay, everybody agree we now have to add 1 to both sides? Well, hold on. We're going to go really slow, but do you agree with me we're going to add 1? Okay, so let's get rid of these here. Okay. So look, y'all, we're going to write, I'm going to do this over here because I'm kind of running out of room. We're going to have y equals x square root of 3. Now, can I write this one as 1 over 1? What do you think? Is 1 the same thing as 1 over 1? Yeah. And anytime I'm combining fractions, don't I need to get a common denominator? And what would my common denominator be here? Okay, so look, we're going to write minus pi over 3. Fix that because it looks a little bit messy. Minus pi over, or pi squared of 3. Now we're adding 6. Okay. 6 over 6. And there we go. Here is my equation. So think about, y'all, the problems that we did on Monday. On the problems we did on Monday, and even Jennifer, the problem that you asked me last night, I sent you the video, right? I kind of followed the same principle. The only difference is in that problem, we had nice, pretty numbers like, we might have still had a fraction or whatever, but we didn't have pi squared of 3 negative plus 6 over 6, right? But the idea is I'm following the same guidelines. I'm following the same principle. I find my derivative and I evaluate it at the value of x that they gave me. That tells me how to find the slope of the tangent line. And then after that, I just use the point that was given to me and now the slope to find my equation. Okay. The only thing that's different about this particular problem is that it's a little bit, more messy because it has pi square root of 3 plus a 6 all over 6. It has something like that. But the principle is still the same, right? All righty. Let's try this one here. Okay. We're going to take the derivative. And I told you guys on Monday, I had that one business calculus class. And when I did fractions, I remember how to find the derivative of fractions because I took that class in 1993. And that professor just really, like, the way he explained it to me, it's like a tattoo in my mind, right? So remember I told you guys we do it like this. Think about that as the bottom. Think of this as the top. And I'm finding the derivative of a fraction. We always take the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom function being squared. Okay? And I never forgot that.
How did you? I mean, assuming you never had any calculus.
You know why? Because he explained it in such a way that was easy. Think about the top and the bottom. To me, that just made so much sense. He didn't say like the numerator and the denominator. He just said the top and the bottom. And I don't know. I guess I just repeated it to myself a bunch of times and I remembered it. No, I swear to God. I swear to God. And guys, I'm going to tell you another little quick story. That professor. So my parents went to UTPA at the time. It was called Pan American University. Now, my parents went to school later on. They didn't go to school when they were 18 or 19. My parents went to school when they were like, early to mid 20s. But when my parents were going to school there at UCRGV, what's UCRGV now, they used to have, just like in high school, you get a yearbook. The university had yearbooks back then. That guy was teaching there when my parents were there. That's how long that guy had been there. That guy was there for a long time. But he was great. He was great. And actually,
He wasn't the department head?
No, he wasn't the department head.
That's crazy.
Because, well, so he didn't have his PhD. He was like me. He had his master's degree. And then, well, put it this way: you're working in a university. If you're going to be kind of move up, you got to have your PhD, right? He didn't have his PhD, but he was actually one of the professors that influenced me to say, you know what? I think I'm going to get my degree in math because I enjoyed his class so much. I ended up taking his business calculus class twice, guys. The first time I barely passed with a C, but it's because I was just lazy. I wasn't doing a lot of my work. But later on, I went back and took it to raise my grade, to raise my GPA. I was like, let me take the same class. And I specifically took him, and obviously, I was like a junior or senior when I took it. So I made an A, but again, I thought he was great. I felt like I learned a lot from him. No. He didn't have a funny accent. Let's go ahead and do this problem, y'all. So look, we're going to take the bottom function, which in this case is 4x squared. We're going to take the derivative of the top. Anybody remember what the derivative of cosine was? Negative sine x. Excellent. Minus, we're going to take the top function, which is a cosine x, times the derivative of the bottom. What's the derivative of 4x squared? 8x, right? Because you got to take the 2 times the 4 and then reduce it by a power of 1. Okay, divided by the bottom function being squared. I'm sorry? Oh, I don't know. It might be because you're underneath the vent. Okay, so guys, I'm just going to do a couple of fixing up stuff here. No, just like that, yeah. So let me fix some of this stuff here. Y'all agree with me that I can write this as a negative 4x squared sine x? I just put the negative out in front, okay. And then can I write this as a negative 8x cosine x? Okay. Now, guys, the reason why I'm doing that, I also don't want anybody to get confused and say, hey, should that be a cosine of 8x squared? No, it isn't, right? You see what I mean? Okay. Last step. How can we rewrite the bottom part? What's 4x squared squared? So what's 4 squared? What's 4 squared? Yes, what's 4 squared? 16, good. X to what power? There you go. All right. And then you got it. You got it.
Do people actually work with you now?
Yes, sir.
Okay, let's say you guys just put the job on to okay, let's say an architect, right? And you're doing building. You actually have like Sine X and you actually like
So you may not, and say like a building, you may not, but in a bridge, you probably will, right? Because under bridges, don't you have these arcs? So in bridges, you may, right? You know, so on point. So you're gonna, yeah, this
doing like the load and stuff like that.
that's right. So yeah, a lot of the stuff. I mean, this is not just done like for the sake of like doing it, right? There's actual applications to everything. So again, guys, like when we talked about in 3.4 when we did that revenue profit thing, right? Easy example was when I was driving today, I saw that taco truck pepper let you just made me laugh. But that's a simple concept where we can apply revenue, cost, and profit, right? And we can say, okay, well, look, if this is how much, this is what my cost function looks like, and this is what my revenue function looks like. And again, those are very simplified versions, but then I can figure out what my profit function would look like, and I can apply those principles to that, right? Okay, so we're going to talk about something called higher order derivatives. So higher order derivatives here, y'all, says the higher order derivatives of sine and cosine x follow a repeating pattern. By following the pattern, we can find any higher order derivative of sine x and cosine x. Okay, so the first problem here says, let's find the first 4 derivatives of y equals sine x. Okay, so this is what we're going to do. We're going to find the first derivative. We're going to find y prime of x. Okay, so my question to you, what is the derivative of sine x? Cosine x. Excellent. Okay. Now we're going to do the second derivative. So the second derivative, this is the notation we use for second derivative. If the first derivative has that little apostrophe, the second derivative has 2 of them because it's the second derivative. And what's the derivative of a cosine x? Negative sine x, right? Good. Okay, excellent. Doing great so far.
Are you going back and forth in the loop?
Well, hold on. We're going to find out. Okay, now we're going to find the third derivative because the directions tell me to find the first 4. So what's the derivative of sine? Cosine. So isn't this going to be a negative cosine x? Right, because I still had that negative there. And then finally, the fourth derivative, y 1, 2, 3, 4. What did we say the derivative of a cosine was? A negative sign. And with this negative right here, what's going to happen? Cancel it out, become a positive. So, quick question, y'all. Do you agree with me that the fourth derivative ends up going back to what the original function was? Okay. So what ends up happening here is we have a repeating pattern. This thing repeats after every how much? After every 4, right? I'm sorry? The 8th derivative would also be sine x. The 12th derivative would also be sine x, right? We can kind of see what the pattern is, right? Yes. No. No. Okay. So now look, we're going to do the same thing here. We're going to find the fourth derivative of cosine x. Okay. So let's try to see if we can do this. No. Don't make it harder than it needs to be. Look, I'm going to show you something. Look, yeah, let's not go Roman numerals or anything like that. If the fourth derivative takes me back to the original function, what do you think 1, 2, 3, 4, 5? What would that look like? It would be the second derivative. So if look, hold on, go slow, guys. If this is the fourth derivative, right, which is the same thing as the original function, wouldn't the fifth derivative be the same thing as the first one, right? And then wouldn't the sixth derivative be the same thing as the second one? And the seventh derivative would be the same thing as the third one, right? You see what I'm saying? Because we're going with that same pattern, right? Yes, there is, and we're going to do that before we leave. That's right. That's the whole point of doing this, right? So now take a look. Let's take a look. Y equals cosine x. What do we say the derivative of cosine is? Negative sine x. Excellent. Okay. Now, let's take the second derivative. What's the derivative of a sine? Cosine, right? So I already have that negative there, so it's still going to stay negative cosine x. Okay. And everybody agrees that the derivative of cosine is a minus sign? And with this negative here, isn't that going to cancel out? So we'd go back to sine of x. Okay, and then the fourth derivative, the derivative of sine is cosine of x, right? So again, isn't the fourth derivative the same thing as the original function? Right? Okay. So now, the question then becomes,
Okay, so is that the what do you call it? That indicates what derivative is?
Yeah, so look, what derivative do we find? The fourth derivative, right? Okay, so now it says using the pattern for higher order derivatives of y equals sine of x, we're going to find the 74th. Okay, so guys, we're not going to sit there and do this 74 times, right? But this is what I'm going to do. So look, this is what we're going to do right here. I'm going to do a little copy and paste again. That's right. We said that these things repeat after every how many? After every 4. So look, I'm going to do this over here. Let me paste this guy right here and paste it. There we go. Okay. So look, this thing repeats after every 4. Okay. And I know I have it zoomed down a lot, but I just wanted to get that so I would have that there. Okay. So the way we figure this out, y'all, because this repeats after every 4, we look at which derivative we're taking. We're taking, in this case, the 74th derivative. So what we do is we do old school math like we did back in elementary school. We're going to take 4 and we're going to divide it into 74. So 4 goes into 7 once. 4 goes into 34 how many times? 8? 32? Yeah, that's what I said. Like we're in elementary school. What's my remainder here, guys? My remainder is 2. Whatever my remainder is, that's the derivative that we're going to use. Right? That's all it is. So you don't have to go through a whole process of, man, do I got to sit there and do this, 74 times? I mean, you could. I wouldn't recommend that you do it, but you could. And so if we're looking at the 74th derivative, it's the same thing as the second derivative. So the 74th derivative of sine of x is equal to the second derivative, which is a negative sign. And that's all you got to do. Does that make sense? Because it repeats after every what? After every 4, right? And so when we have that idea of repeating after every 4, you can say, well, look, we can go through these. How many cycles of 4 are there? Well, there's 18 cycles of 4, and then we got to go 2 more. So that means we're back at the second derivative.
So, wait, is the remainder always going to be 1 through 4?
Yeah. So look, good question. Let me do this, y'all.
Because it's been so long since I've done algebra, I don't even remember like the principles of it. Like I just know the emotions, you know what I mean? And like the course Christian.
Okay, so look, let's do another one here. Let's do the 76th derivative, okay? If we were going to find the 76th derivative, we would have to take the number what? 76, and we would divide it by 4, right? So we already know that's going to go in 1 time. This is 36. Okay, how many times does that go in? 9. My question to you, though, what's my remainder? 0, right? And didn't we say whatever my remainder is, that's the power that I'm going to use? Okay, so look, I'm going to ask you a question. Could I do this? Instead of me saying it goes in 9 times, could I say it goes in 8 times with a remainder of 4? Would that still work? Because 4 times 8 is 32, and if I subtract, I have a remainder of 4. The idea, guys, is if you have a remainder of 0, it's the same thing as having a remainder of 4. Okay? So when it goes in nice and pretty, like the way it really the 19, it goes in nice and pretty. That's the same thing as having a remainder of 4. A remainder of 0 and a remainder of 4 mean exactly the same thing. Okay? There's no difference in them. Right? Now, when we were back like in 2nd grade and we did this here, anybody remember why they told us this was not correct? Because my remainder has to be smaller than my divisor, right? That's why they told us that, right? But principally it's the same thing. Okay, it's mathematically it's the same thing.
You have to drop down to 0, 40, divided by.
Okay, let's try another one here, Go. So let's take a look. F of x is equal to 3 sine x over 3 plus cosine x. We're going to find the derivative. Okay, remember, y'all, I'm going to do it like this. That's my top function. That's my bottom function. So when I find the derivative, it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom function being squared.
They're very similar. It's like you have cosine x, sine x, and sine x, cosine x over tan.
Okay, so let's go through one piece at a time. We're going to take the bottom function. Everybody agree the bottom function is 3 plus cosine x? Okay. Now, we have to take the derivative of the top. Anybody know what's the derivative of 3 sine x? I'll give you a hint. Still going to have a 3. What's the derivative of sine? Cosine, right? Boom. So guys, remember, if we have a number in front, it's still going to be that number times whatever the derivative of my function is, right? Minus the top function. So the top function is a 3 sine x. Now we got to take the derivative of the bottom. So we're going to do this in pieces. What's the derivative of 3? 0. So we don't got to worry about that part. What's the derivative of a cosine? Negative sine x, right? All divided by the bottom function being squared. So I'm going to put 3 plus cosine x all squared. Okay. All right, we are going to do a little bit of algebra here, guys. And the reason why we're going to do a little bit of algebra, I want to scroll back to the problem. I want you to notice in the particular problem that we have, y'all, it does tell me to simplify my answer. That's why I'm going to do a little bit of algebra here. I'm going to go ahead and like multiply some stuff out. Okay, so look, we're going to go slowly. We're going to take this guy, 3 cosine x, times 3. What is 3 times 3 cosine x? 9 cosine x. Good. And now we're going to take 3 cosine x times another cosine x. That would give me a 3 cosine squared x, right? So the x is not being squared, the cosine is being squared. Okay. All right. Now, take a look at this next part. What is a negative 3 sine x? Or, sorry, a minus 3 sine x times another negative. A negative times a negative? Positive. 3 sine x times another sine x? There you go. Okay. On the bottom part here, you guys, I still have my 3 plus cosine of x, the whole thing being squared. Okay. All right. We're going to keep working here. So 9 cosine x plus, I'm going to show you guys something here. Do you agree with me? Out of those two pieces, can I factor out the number 3? Do they both have a 3 in common? If we take out a 3, wouldn't we be left with cosine squared x plus sine squared x inside those parentheses? Okay. Now, again, I'm not certain how much of like trig identities you remember. And guys, that's equal to 1. Very good. Okay, so y'all, I'm going to show y'all something real quick, and I'm going to upload this. I'll do it at the end of class, but let me come back over here. Okay, so I made these notes last semester when I taught pre-cal, but I'm going to upload this, y'all, into our folder so that you guys will have access to all this kind of stuff too. It's just like trig identities and stuff like that. And I know some of you, like I know the only reason I'm picking on John because John was in my pre-cal classes last semester. So I know John probably has a fresher fresher experience with this. I don't know the last time any of you guys saw trig stuff, but I'm going to provide this for you guys so you guys will have access to it as well. I'll upload it in this week's, business too, guys. Okay. But if you look right here, Pythagorean identities, sine squared x plus cosine squared x is equal to 1, right? That's what we're using right there. Okay. So now what we're going to say is this goes to 1. That's right. So now what we're going to have, you guys, we're going to have f prime of x is equal to 9 cosine x plus 3 all over 3 plus cosine x all squared. This right here, you guys, is good enough for you guys to stop. Okay. I did the problems before I came to class, and this is good. You can leave it like that. But you do want to simplify some of those pieces, though. Okay, you do want to simplify some of those pieces. Yeah, you can do more. You could foil out the bottom part, but you don't need to. That's why I just said this is good enough. When you're going to enter in your answer, and on my on my open math, this is good enough. No, you gotta fold it out old school, long way. Yeah. Okay. Well, that's why I said that part there is good enough. Okay. Okay. So I'll tell you what, you guys, there is, yeah, we got time. It's just 2 problems. These are the last 2 problems out of 3, 5. I was gonna say let's stop, but let's go ahead and just do these 2. It's only 2 more problems, and we can definitely do this. It's not a whole lot there. Um, so we have something here called motion along a line. So it says another use for the derivative is to analyze motion along a line. Velocity is the rate of change of position. So we take the derivative of velocity, we do find the acceleration or the rate of change of velocity. And we'll talk about speed, which is something called the magnitude of velocity. Okay, so let me tell you what we're looking at here. This is our original function. S of t is just the position equation, okay? So a lot of times we do in algebra, and you may remember this, maybe you don't, but in algebra they often talk about, oh, we have an object, we throw it up in the air, and the equation is parabolic, and because it goes up and then it comes back down. And if you think as time goes along, it's getting higher. As time moves this way, it's getting higher and higher and higher, and then it comes back and hits the ground again, right? So we often have a position equation. If we take the first derivative of that equation, we end up with something called the velocity, okay? The speed is just the magnitude of the velocity. The velocity, you guys, is an equation that has like direction and stuff like that. The speed is just, if it's going up, at what rate is it going up? If it's coming down, at what rate is it coming down? Okay. And then we have something called the acceleration. The acceleration is actually the second derivative of the particular function. Okay. So I'm going to show you what I mean by all this kind of stuff by doing this problem. It says a ball is dropped from a height of 64 feet. Its height above the ground in feet, t seconds, is given by this equation. Okay, so the question says, part A, what is the instantaneous velocity of the ball when it hits the ground? Okay, so one thing I want you to notice, there's a couple of ways we can do this problem here. When it hits the ground, the position is actually equal to 0. Okay, so what we want to know is, when is it going to hit the ground? So if the position is of the height of the ball is 0 when it hits the ground, what we're going to do, we're going to take this equation here, and we're going to set it equal to what number? 0. So we're going to write negative 16t squared plus 64 is equal to 0, and we're going to solve for t. Okay. So first question, do you agree with me that if I move that 64 over, it's going to become what kind of 64? Negative, right? Okay. Second question, what do you think we need to do to get rid of the negative 16? Divide by negative 16? Okay. And are you coming up with t squared is equal to, what's negative 64 divided by negative 16? Positive 4, right? Okay. What do we need to do to get rid of the square? Square root it? Okay. So everybody agree t equals 2? Okay. So it's going to hit the ground after 2 seconds. Now, I told you guys, there's 2 ways you can do this problem. The reason why I wanted us to do it this way is because this is the algebraic way of doing it. The other way, guys, could we have not looked at the picture and said, hey, look, it hits it at 2? Yes. But you may not always have the picture, right? In this case, we had the picture. Yeah, it works nice and neat. But look at the equation we solved. It wasn't like it was, you know what I mean? We weren't solving anything major. Okay, now, when we're going to find the instantaneous velocity, that means we're going to take the first derivative. Okay. If we take the first derivative, what's the derivative of 16t squared? Anybody know? What's the derivative of negative 16t squared? Negative what? 32 with a t? And then everybody agreed that the derivative of 64 is 0? Because I'm finding the derivative of that function? Okay. What we're going to do now, y'all, we're going to evaluate that at 2. So the instantaneous velocity, negative 32 times 2 would be negative what? Negative 64. Y'all, the units here are going to be feet per second. It's going to be units in whatever my height is being measured in over units of whatever time measurement we're talking about. If you look at my time measurement, T stands for seconds. When you guys are driving to school or you're driving home, if all of a sudden you're driving and you see the red and blue lights behind you, right? And they pull you over and they say, hey, I clocked you at 87 miles an hour in the construction zone, right? It's miles per hour because velocity is always measured in units of length divided by units of time. You see what I mean? So that's what velocity is, right? Now, you know why this one here is a negative? Because the ball is going which way? Down. Okay. So if we were saying what's the speed of the ball, we would say the speed of the ball was just 64 feet per second, but the velocity tells me the direction, that it was going downwards as well. Okay, that's really the difference between the speed and the velocity. Now, there is a part B, okay? Part B says, what is the average velocity during this fall? So this is what we're going to do. To find the average velocity, I'm sorry? I can't hear what you're saying. Okay, we're going to get to that part in a second. During the average velocity of its fall, kind of like the slope, yeah, we're going to find the position at 0. So remember what our equation was? Our equation was s of t equals negative 16t squared plus 64. So if we do this, everybody agree that's at 64? Okay. So at t equals 0, the ball was at 64 feet up in the air. Okay. Didn't we find that s of 2 was equal to 0? Because we did that right over here. We said that it was going to be equal to 0 after 2 seconds. Okay. The way we're going to find the average velocity is we're going to take the difference in these heights. 64 minus 0 divided by the difference in that time. 0 minus 2. So what's 64 minus 0? 64. What's 0 minus 2? Negative 2. Isn't 64 divided by negative 2 the same thing as negative 32? Guys, remember, this was my height. Wasn't this being measured in feet? So this is feet. This was my time. Wasn't that over a 2-second period? So the average velocity and the instantaneous velocity when it hit the ground happened to be the same. Okay. The average velocity means let's find the rate of change in the height over that time interval. Okay. Okay, so y'all, we got one last question to do here. And it says, let s of t be equal to 6t to the third plus 36t squared plus 54t be the equation of motion for a particle. Find the function for the velocity. The velocity, y'all, is my first derivative. Okay? So what I want to do here is I want to find s prime of t. S prime of t is the same thing as my velocity function. Okay? So we're going to go through this in pieces. First question. Does anybody know what's the derivative of 6t to the third? 18t squared. Good. Second question. Anybody know what's the derivative of 36t squared? 72t. Excellent. Last part. Anybody know what's the derivative of 54t? 54. There you go. Notice how we did it, guys. We went one piece at a time. We went real slow, right? Okay. Now, look at the second part of the question. The second part of the question says, when does the velocity equal to 0? So what we're going to do is we're going to take this equation that we just came up with, and we're going to set it equal to 0. Okay? And they were nice enough to give me a hint. They said, can we factor out the greatest common factor? 9 looks like it's going to be the greatest common factor. Actually, 18. Couldn't we take out an 18? Okay, so look, we got a t squared. Anybody know how many times 18 goes into 72? A little bit more, I think. 4. Okay. Anybody know how many times 18 goes into 54? 3. Good. Okay, now for the next part, y'all, this is when we're going to do the factoring part. Now, I may have told you this before, maybe I didn't. When the number in front of the t squared is a 1, these are the easy breezy cover girl problems to factor. Because all you're going to ask yourself is, what two numbers multiply to 3 and add up to 4? What numbers multiply to 3? 3 and 1. And do you agree that they add up to 4? Okay. So when the number in front of the t squared is a 1, after we factored out that 18, they should be easy for you to factor. Okay, now y'all, this is just a college algebra type problem. I want you to notice, do you agree with me that we're multiplying here? Okay, when we multiply 3 numbers together and we get 0, one of those numbers is going to be 0. But you know which one is not 0? Yeah, it's 18. So I'm not going to worry about it. I'm going to set the t plus 3 equal to 0 and the t plus 1 equal to 0 because those parts have the variable part. The 18 is always going to be 18. But these parts might be equal to 0. If we move that 3 over, what kind of what number would we get? Negative 3. And when we move this one over, what number would we get? Negative 1. Okay? So we came up with two numbers, negative 3 and negative 1. Okay? So look, y'all. Look at the part B to this question right here, which is this part. When is the velocity equal to 0? Negative 3 and negative 1. Which one do you put first? It doesn't make any difference. Okay? All right. And then the last part of the one that we have here, y'all, says, can we find the function for the acceleration? Okay, so look, I'll put this part back up in case you all still need it, but I want us to look at the acceleration. The way we find the acceleration, y'all, the acceleration function is the second derivative of the position or the first derivative of the velocity. Okay, so what am I doing now? I'm going to take the derivative of the velocity function. I'm going to take the derivative of this guy right here. So we're going to do it piece at a time. What's the derivative of 18t squared? 36 with a t. Excellent. Okay. Then we're going to do the second part. What's the derivative of 72t? 72. And then what's the derivative of 54? There you go. And you got it.
So, define the acceleration of an object.
You take the second derivative of the original function, or you take the first derivative of the velocity. Yeah.
How do you explain the second derivative? It's not the same thing as
Well, look, isn't this my original function?
yeah.
We took the first derivative, so if you take the derivative of this again, that's the second derivative of that function, because you took the derivative twice. Right?
If you put the same derivative, it would just be 36, right?
It would just be 36, yeah. But in terms of like physics, it doesn't really tell you a whole lot, right? The first derivative tells you velocity, second derivative tells you the acceleration. So guys, I am going to stop recording the session, and like I said, I'll upload